The false position method. In this lecture, you're going to discover that the false position method is essentially the bisection method. We just make a better calculation of where the root might be than just bisecting the upper and lower bounds. So we'll talk about the methods. We'll derive the equation that we estimate the position of the root better than the bisection method and talk about that a little bit, and then finish with some notes on the implementation of the false position method. Description of the method. So we start very much, well, exactly like we did with the bisection method. We have some function that has a root somewhere, and we define lower and upper bounds, and we calculate the function at the lower and upper bounds. Now, the bisection method will estimate the new root as the midpoint between the lower and upper bounds. But what we can see is that the actual root is way over to the left. And if we could somehow use any information from the function, we would know this and we could make a better guess as to where that root might be. That's the false position method. We essentially fit the endpoints at the bounds with a line and figure out where that line would cross zero. Now, the actual function we're root finding on probably isn't a straight line, so we'd be off by a little bit, but when we iterate, we close in on it much faster than the bisection method. Now, this greater efficiency we also pay a cost for. If the function happens to be highly nonlinear, then a linear approximation can actually lead to some problems and even lack of convergence of the algorithm. So we pay a price for that efficiency. Let's just go through a few steps. And so we start with defining an upper and lower bound. And we need to make that so that it spans a single root. And here we're showing the function. It's a little bit nonlinear-ish. And here's the actual root that we want to find. So the first thing we'll do is take the points at the lower and upper bound and pretend that there's a line connecting them. And where this line crosses zero, that is how we will estimate the position of the root. And the more linear this function is, clearly the better that guess will be. The more nonlinear it is, suppose the function, for example, stayed pretty low and then spiked up right here at the end. This is going to be a very bad estimate because the actual root would be over here somewhere. But for functions that are near linear, this is a very, very effective way of evaluating where the estimate is. I will also mention we could potentially evaluate a third point in there, calculate a polynomial, and figure out where that crosses zero as our new estimate. So you can imagine other variants of this method. Okay, so we made a guess based on that line where the line crosses zero, and we will evaluate the function at that new guess for the root. At this point, we will adjust the bounds, just like we did for the bisection method. We're looking at the sign of the function at this new root and also the sign of the function either at the lower or the upper bound. We did it by comparing to the lower bound. And then whether we know whether to adjust the lower or upper bound. In this case, we're moving the lower bound up to our new guess. Then we connect this new point to the point at the upper bound with a straight line, and that gives us a better guess, and we're closing in on it very, very fast. And so this goes on, and this requires much fewer iterations than the bisection method for functions that are close to linear. Let's derive the equation that we're using to estimate the root. So we start just with the equation of a line. So we will need the slope, and we will need one point somewhere on the line that we're writing as x naught, y naught. That's an equation for a line. So if we assume that the function between the upper and lower bounds is linear, or at least we'll approximate it that way, then the slope being rise over run is simply the function at the upper bound minus the function at the lower bound. This is the rise. And then the run is the x value at the upper bound minus the x value at the lower bound. So that's the span between the points. So rise over run, that's the slope of the line connecting the function value at the lower bound to the function value at the upper bound. So let's choose the lower bound to be this one point that we know on the line. So we now have a point on the line and the slope. And so here we're plugging in our slope. We're also plugging in our y value at the lower bound and the x value at the lower bound. So we estimate the position of the root by setting y equal to 0 and solving for x. And we will interpret that value of x, which is right here, as the guess for our root. So that's the new guess for our root. And we get this equation. And we got that equation by letting the lower bound be that point x naught, y naught. Now we're going to do the same thing, but now we're going to let this point x naught, y naught be the upper bound. So we now have the y value for the upper bound, the x value for the upper bound, and then the same slope that we had. Just like before, we'll estimate the root by setting y equal to 0 and solving for x. And here's the value of x that we'd be solving for, and we will interpret that as the new guess to where the root is. And so we end up with this equation. So at this point, we have two equations to guess where the new root would be. And in fact, both of these equations work and they'll give us the same answer. But we're going to do something neat with them that will help us interpret what's happening here and compare it to the bisection method. So let's average those equations. They give us two guesses at the roots. Let's add those two and divide by 2. And if I simplify, we end up here. And if we look at this long enough, something sort of magical happened. Here's that equation. The first term, if we only have that first term in the equation that we just calculated on the previous slide, this is the bisection method. If we then tack on the rest of that, this is clearly the correction term that makes the false position method better than the bisection method. And this form I really like. This is what I implement in my codes because it gives me a way to convert back and forth between bisection and false position method. If I want the bisection method, I only do this. If I want false position, well, then I add on, or I guess I should say subtract, this other term. Notes on implementation. Let's step through a block diagram of the false position method. So we start the algorithm with, of course, the function, and we choose these lower and upper bounds that span a single root. The next thing we'll do is evaluate the function at the endpoints. And remember, keep this mentality that every time we evaluate the function at a value of x, that could take a week or at least a very long time. So we want to minimize the number of times we call this function. So anyway, we have to evaluate it at the upper and lower bound, so that's 2 calls to our function. At this point, we estimate the position of the new root, and we're using our equation for the false position method, and I've sort of color-coded it to show if we just have this first part of the equation, that's the bisection method. If we add on the second part of the equation, that makes it the false position method. But for false position method, we're doing this whole equation to estimate the position of the root. Now we enter the main loop, and the first thing in the loop we want to do is evaluate the function at this new estimate for the root. We will then multiply the function value at the lower bound times the function value at this guessed root, and we're not so concerned about the number values, it's the signs that we're caring about. So if we multiply those together, one weird thing could happen. If we happen to land right on the root, then our function value at that root is 0. And, well, of course, we're done. And I always add that to my codes because I think I have a memory of it happening once, but it's unusual, but it's in my code. More often, we need to check the sign of this. If the sign of that product is less than 0, that means that the function value at the lower bound and the function value at our guess at the root are different signs. That must mean that the actual root is somewhere between those two, in which case we want to move the upper bound down to the guess at our root. And notice we're copying the information over. We're not being lazy and just reevaluating the function because we've already done that. And this could be a week's worth of work. And so we just copy that over so it's essentially instantaneous and we don't have to call that function again. On the other hand, that product could be positive, meaning the function at the lower bound and the function at the guess at our root have the same sign, which means that the actual root has to be to the right or towards the upper bound. And so we need to take the lower bound and move it up to where the root is. So we just copy the information over from the root to the lower bound. And we're not being lazy and reevaluating the function at the lower bound. We're just copying that information over from the function at the guess at the root, which we've already calculated. Given that we've adjusted our bounds, now we go ahead and calculate the new guess at our root. And we're using this color-coded equation where the black on the left is the standard bisection method, and this other term makes it the false position method. And I'll point out, this blue part of this equation, this is the only part that makes the false position method different than the bisection method. So it's very easy to convert it over. So given this new root guess, what I will do is subtract the new root minus the old root. So new root minus old root, and we divide by the x value, either the new or the old. We're essentially just normalizing it. So we're looking at percent change from iteration to iteration. And so we calculate that percent change and we compare that to a tolerance. If that amount change is greater than this tolerance, so we're still making very big steps, we will go back and evaluate the function at the new root and everything repeats. We adjust our bounds and so on. If that adjustment falls below some tolerance that we've defined, then the algorithm is done and we've finished. Now, the false position can actually fail, and this fails when we have a very, very nonlinear function, and this linear estimate does a very bad estimate, and we end up way off somewhere in the middle of nowhere every time we try to calculate this estimate. So if things are very, very nonlinear, this can fail. So here's one modification you can do to your code. You can track the number of iterations, and if that becomes greater than something like 1,000, then maybe revert back to the bisection method and you multiply that little addition, the blue part of the equation on the previous slide, maybe you multiply that by 0. That just automatically turns your function into the false position, the bisection method, and then you can close in on the root. So for very nonlinear functions, this can fail, and that's the price we pay for a faster algorithm. We'll end this with some final notes on the false position method. So the false position method, I would say, is exactly the same as the bisection method. Well, not exactly the same. When we calculate or estimate a update of the position of the root, we have a more intelligent equation here than we did for the bisection method. And that's good and it's bad. It's good when our function is very linear, we can converge in much fewer steps, but that also can lead to problems and actually go unstable or even converge more slowly for nonlinear functions. So it does this by using more information. We know the function value at the lower and upper bound. Why not use that to calculate a more intelligent guess as to where the root is? And that's the magic behind the false position method that the bisection method does not do. So for linear functions, this is awesome. This converges very, very fast, many fewer iterations than the bisection method. However, for highly nonlinear functions, it can converge actually much slower than the bisection method. And sometimes it doesn't even converge at all. And that's the price we pay for a more efficient algorithm. And that just seems to be the trade-off we always have to make. We can do something faster, but there's always a price we have to pay for that speed.